next topic, attention and eye movements, and let's jump right into it. This is a mental image of how I thought about eye tracking when I started doing eye tracking 2 years ago. It's a really fancy device, and it's capturing attention, and it's just more or less plug and play, and there you go, you have it. Very easy. In fact, I think probably even the first, even second, maybe third paper, I don't know, I kept confusing the word attention with the word eye movements. And, well, I don't know, some papers later I decided I'm just not going to use the word attention anymore. So I'll stick to the operational definition, which is eye movements, and try to think about what is it and how can we predict it, what's the consequence of different eye movements on decision making, which is my research topic. But then Catherine asked me, well, let's talk about attention and let's talk about eye movements, so now I have to think about it again. What is it actually? But yeah. Then I thought back, well, this is how I imagined it. It's a really fancy device, and it's capturing attention. But then later, I'm realizing, well, it's also capturing other stuff. So, for instance, if you look in the literature, eye movements have been used to identify all sorts of interesting constructs like decision processes, anxiety, deliberation, confusion, heuristics, memory, emotion. You mentioned. You can probably make up some more yourself. But of course, what it's mainly measuring is just eye movements. So how we move our eyes around in the visual environment. So how are we going to figure out whether, how, when it measures attention? I wasn't really sure what kind of take I would have on this, but I sort of hoped that Josh would have figured it out for us first, and then I could just build on that. And I think, well, my first argument will be actually eye tracking does not really measure attention. It's very much up to the experimental design what we make with it. So it can possibly measure attention. Now, of course, I will elaborate on this, so don't worry. Otherwise, we can stop now. So when you see that list, and possibly the list is even longer of things that you can use eye tracking to study, you're probably wondering how is it even possible that in one experiment you can use it to study self-control or communication or memory and emotion and so on. How is it possible to study all these different things with just eye movements? I think the trick is really to understand the importance of the experimental design and its role in borrowing alternative interpretations. So eye movements can possibly map onto a lot of different constructs, and the only way that we can get to it mapping onto attention, because that's really what we want, is by excluding other things. I believe, at least. But let's carry on. I guess it's important that we are all on the same page. So what is eye tracking actually? And I have just this one slide to explain to you what eye tracking is. And it's probably very complicated stuff that's going on behind the scene, but usually I don't care too much about it. That's stuff for engineers. But it is a device that, with the help of infrared light, somehow captures the image of the eye as you're in the kind of research I do, looking at a computer monitor. And behind the scene, you have some different things going on here, and in a way it's sort of just trigonometry, figuring out, based on some calibration points, where are you currently looking. So you send infrared light into the eye, and you, with that camera, basically measure the reflection of that infrared light. And usually what the eye tracker is actually looking at, the camera in the eye tracker is tracking an image like this, and you can see the infrared light and an image of the pupil. And I don't know, maybe there are some people here who are actually more familiar with the mathematics of it, or the engineering part, maybe, or maybe not. Just, I think it proves the point that you can do eye tracking, you don't need to know the engineering part of it, although of course it would be cool. But in essence, it's simply a fancy device that captures the position of the eye while you're looking at, for instance, a screen or somewhere else in the environment. So I don't want to dig much more into that, because what we actually want to talk about is, now that we have a device that can measure where we're looking, how then do we use that to study attention? I guess that's what we're here for. Right? So the way I've thought about building up my argumentation is actually rather not so much saying this is how you measure attention, but rather saying this is how you do not measure it. So outlining somehow the assumptions and the boundary conditions that we have to think about when we want to use eye tracking to study attention. And the first boundaries that you run into with eye tracking is there's a whole bunch of different error sources related to eye tracking. And this is possibly the topic for another workshop on actually how to do eye tracking. But there's a lot of things that you need to think about technically. And I just want to give you a glance at it. I don't want to actually dig into it, because what I really want to talk about is what we could call the researcher-related error sources. So when you plug in your experiment and you start running your eye tracking session, are you actually measuring what you think you're measuring? This is one of my favorite examples. It's from a journal in, I don't remember what paper and whatever journal, doesn't matter, but what they want to study is, do people have what they term an attention bias to this thing here, which is supposedly also called brain porn. So not so long ago there was some people figuring out that if you put some brain porn in your articles, then you're much more likely to get it published and people will cite it more, and you're more likely to get the Nobel Prize and I don't know what. So if you have a boring bar graph, then what you should really do is replace it with this kind of fancy brain image, because that's like instant coolness in your paper. So they wanted to figure out in this article here, do people have an attention bias to this kind of brain porn, right? And does that then predict how cool they think this article is and how likely they are to cite it? So they make a very simple experiment. They basically just manipulate these two things here. In this location, they either insert a bar graph saying one thing, or they insert this brain porn image. And then they measure the number of fixations to this location here, and they get this result. And surprisingly, I assume, to the authors, they find out that people have more fixations to the bar graph than to the brain porn image. But that is totally against the hypothesis, right? The hypothesis is people have an attention bias to brain porn, right? Because people love it. It's interesting, it's fascinating, it's instant coolness. So how is it possible that the results actually indicate people look more at the boring bar graph? Bummer. Well, the reason I believe is, when you set up an experiment like this, you're basically comparing apples and oranges. So it's a kind of no-go when doing eye tracking that personally I would think is related to not having thought about what you're actually measuring. Possibly you can imagine, why would people look longer at the boring bar graph than at this image here? Any ideas? Okay, there are many ideas. Anybody?
Well, I would think you're spending more time trying to actually interpret the data in the graph, whereas most people would give up on trying to interpret anything out of the neuroimaging.
Exactly. Yes. You simply just to understand any graph, you need to at least have read the x-axis x-axis labels and the y-axis labels. And then you need to look at the content too, right? So there are at least a couple of different locations and some text you need to process. The real reason, or I believe that the reason why you get so different results is basically the same reason as, it's like putting in a 100-word text here and a 500-word text here, and then you expect people to look longer at the 100-word text. They wouldn't, right? You need longer time to read more text. And the same is true for things that are more difficult to process. It's easy to process this kind of image, possibly, but it's difficult to process a bar graph. Actually, it's so difficult that people dedicate their whole career to figuring out how to make it easier.
That's a questionable statement, I'm sorry. This bar graph is only, one is larger than the other. You could just happily see this is larger than that, I can go on. And to process that image, you have to know quite a bit about the brain. And it's also visually more complex in terms of, exploring this with your gaze and seeing what is what. So it's purely visually, it's not an easy image.
Yeah, maybe you're right. You have a
Unless
counter-hypothesis.
you're a neuroanatomist.
But either you know something about the brain or you don't.
Exactly.
I will
Yeah,
not
that's what
learn
okay,
anything
so
about
if-
the brain by looking at that brain.
So that's what I'm saying. It depends on who you are. So it's only easy for people who know something about the brain to process that. In that case, parts of the frontal lobe do something. For others, it's probably as bewildering as anything else that you haven't seen before.
But they will know from looking at it that it's okay. I know that there's a dot.
Okay.
That's it.
And then you know it's 2 bars. So
But you're completely right. You're pointing to an important point. I mean, what is easier and difficult for people to visually process depends on your level of expertise with that kind of imagery, for instance.
I didn't mean
And,
to interrupt. So
No, but it's a good comment. Thank you. I suppose that in this case, most people found it easy to identify there is a dot here, there's no dot there. Okay, fine. But then at least here you need to read the axis labels, and well, actually it is rather simple graph. You're right.
But there's also a number of fixations. There's only one thing to look at in the brain.
True. Well, anyway, I hope the point is clear. If you just plug some stuff into your eye tracking experiment and you claim that you're measuring attention, well, you're measuring all sorts of processes that are actually driving eye movements. And yes,
Can I just make one more point about the number of fixations? I mean, that being just one measure, you could have one really long fixation on the dot on the brain and lots of small fixations on the graph, and it's a good point building on what you said, that you need to be careful of what you're measuring and what the measure actually relates to.
I remember having had similar discussion with the Pony Lab members not too long ago, and because you actually wanted to do something like this, right? Is it okay for me to say?
Yes,
Right.
yes.
Comparing apples to oranges in a way. So how do you actually do that? Right? Can you, in a way, do it? But I think you found a solution at least, right? But I mean, and I guess I can hint here. The trick is not to rely on just one operationalization. Right? So if you just compare one image to one other image, that's not okay. But maybe you can think of it. You have multiple images, and hopefully some of the differences will randomize away, but I don't think they would ever randomize away with an image versus a bar graph, even if you had 20 bar graphs and 20 brain images. Yes.
Sorry, can I ask something? The way this experiment was operationalized, they did they change the text as well as the figure?
Well,
Because it's
actually,
hard for me to think of the text saying see figure 1 and then directing to the same, because it's different pieces of information actually, right?
yes, they must have changed the text. So I basically copy-pasted it out of the article. This is a figure illustrating their experimental design. So they were changing the caption, obviously, and some of the text that refers to the image. Yeah. Yes, of course you have to change more than just the figure. Okay. So how to do this and how not to do it. What I actually want to talk about, and I don't want to talk about how it can go wrong, or maybe actually I wanna, but I want to start by talking about some assumptions, or I like to call them auxiliary assumptions. And the first one is that if we think we want to measure attention with eye tracking, then I would claim, or I would believe, that you need to make at least one assumption, that one being that people are actually processing or attending to what they are currently fixating. Or if you want to phrase it negatively, people are not processing what they don't fixate. And one version of this assumption is also known as the Imind assumption, and this was developed in reading research, where some clever people figured out that fixations very neatly correspond to how long time people need to process words, different words. Now, technically, this strict sense of the Imind assumption has actually been falsified. So how can you still make it? Well, I personally think that we keep making it, or a lot of people at least make it, or have to make it, implicitly or explicitly when conducting eye tracking research. We have to assume that people are processing what they're fixating. Now, the other assumption that I want to talk about today as well, it's a bit more in a way on the data processing side or technical issue, is that 99% of the eye tracking research being done is relying on another assumption, which is that there is a one-to-one mapping between a fixation and an object. And this probably sounds really strange right now, but I will give you examples later. So we can just forget about the second assumption for now. But these are the two assumptions I want to talk about. I want to talk about the boundary conditions for these assumptions. So in a way, you could say, how do you measure attention with eye tracking? Well, first of all, it depends on how you design your experiment, but even if you have hopefully thought of a very nice experiment that bars alternative interpretations, then there are still some assumptions you need to make and some boundary conditions. And this is what I would like to go through now. So let's start with this assumption first, called the Imind assumption. And the Imind assumption, the original version, basically states that there is no appreciable lag between what people fixate and what they are cognitively processing. In other words, what you're looking at right now is what you're mentally or cognitively processing. So if I look at you, I'm cognitively processing you. If I look at Catherine, I'm cognitively processing Catherine. If I go forth and back looking between you and her, then now I'm processing you, now I'm processing her, and so forth. I cannot process her while looking at you. Of course, anybody can realize that cannot be true. I can think about Catherine while looking at you. Okay. So, point falsified already. But still, we are making this assumption. And why do we make it, or how can we make it? Well, the basics of eye movements is, I will only talk about two different eye movement behaviors. And they are termed fixations and saccades. Fixation is when the eye is standing relatively still on some location, and a saccade is a fast movement that the eye makes to some new location. And I pretty much always use this illustration. I think it's brilliant. It's actually from a Toby white paper. And besides this idiotic representation in the brain, which is probably not there, then the point is, if you fixate, or we have a viewer and he's looking at this image here, he starts out by fixating this location, then the eye jumps to that location, and the fourth location. Now what the eye is actually seeing is, during the first fixation, he will see a very clear image just in this area, and everything else is a blur. When he moves the eye to the next location, this location will get into focus and everything else is a blur. So the old location, the previously fixated location, is now a blur. Right? And this may be surprising if you haven't really thought about the phenomenology of seeing things before, because usually we just have the experience that everything is visually clear to us, right? Everything seems clear, sure, right? But of course, it's very easy to convince yourself that if things are in the visual periphery, it's harder to actually identify it, right? So if, say, Catherine were making faces and or something, well, how close to her would I need to fixate in order to actually see it? Can you make some faces?
No.
Well, the thing is, I actually need to fixate almost directly at her to see if she's making funny faces at me. So the fovea, the center of the visual field where we can see things clearly, is only 2 degrees of visual angle. And this corresponds to the width of your thumb when you're stretching your arm. And this trick is fortunately independent of how long your arm is, because it scales with the size of your thumb, unless you're a harbor worker or something. So for most people, the width of your thumb is exactly 2 degrees of visual angle. So this is the area in which you can see things clearly. Everything else is actually a blur, more or less. And the blur gets bigger the further you go to the sides.
Sorry, it's
Yes.
2 total or 2 from the center?
Sorry?
2 in total or 2 from the center? So
The radius or the diameter, you mean?
yeah. So is it 2 like this or 2 like this?
I'm not. The diameter.
Is the
It's
whole
neither.
thumb two angles right?
If
or
you
is
have a
it
focus
four
as a dot,
actually?
the 2 degrees count to the left and to the right, or in total. So 1 to the left, 1 to the right from the center.
It's the diameter. So 1 to each
Okay,
side.
so it's a sector. Okay. Good.
Yeah.
Yeah, thanks. Just to
Okay, yeah.
Because I always thought it was 1 from the center.
Well, actually, it's not exactly 2. It's 1 point something,
Yeah, yeah.
almost. Right.
1.5,
But outside the fovea, you have paraphobia, which has slightly impaired acuity, but it's, well, actually, acuity drops incredibly fast. It's basically, what is it, exponentially dropping. So as soon as you get outside these 2-3 degrees, it's very hard to actually identify many things. So in a way, you could say this is the, whether we know it or not when we're doing eye tracking, this is what we're somehow building into the study. We are sort of relying on the notion that our participants, when they sit in front of the screen, are only visually processing what's within 2 degrees of visual angle. And in many cases, we will actually design our stimuli in such a way that it's separated by at least a couple of degrees of visual angle. In this way, you know that if I'm looking at object A, then I can't at the same time identify object B, because it's more than 2 or 3 degrees of visual angle away from that object. So that's a neat way of somehow utilizing the fact that we have such poor vision. We can only see clearly in the fovea. But there's obviously more to it. So you could say this is what, in a way, proves the eye-mind assumption. We have a fovea, we can't really see much of what's going on in the peripheral visual field, but that's unfortunately not entirely true either. So let's take this example here. So I would like you all to fixate this red cross and maintain your eyes on that red cross. And now tell me, I will show you an image of a street, and there's a boy crossing the street. You just have to tell me whether he's to the left or to the right, and keep looking at that cross. To the right? Okay, well, try and move your eyes around. So hopefully this simple example illustrates one of the problems in identifying what can we see in the peripheral visual field. The reason why you probably didn't see the boy crossing the street here is that he's being flankered by 2 objects that have the same color as his shirt. And this effect, this flanker effect, makes it hard to identify objects. So here's something that in a way works in your favor. When you do eye tracking, you can use this flanker effect. But on the other hand, there are other things that work against you. So for instance, if an object is being scaled in size or contrast, then you will still be able to identify it in the peripheral visual field. So this map here shows you the exact amount of scaling that you need in order to maintain visual acuity. So if you fixate in the middle of this circle here, then every letter or every circle of letter should be equally identifiable. So this map actually tells you in a somehow visual way how much you need to scale up things in order to be able to still read them.
So if I can't read the letters in the middle, what's wrong with me?
Well, maybe you need to go to the optometrician. No, actually, I can't
You need to standardize the distance that you view it from.
read. Yeah, the distance has to be right, of course. Actually, I don't know how much with this size you would need to stand away from it, but it's more or less what you're doing at the optometrician. If you go to the optometrician, he will show you different letter symbols and so on, and you have to basically read them as they get smaller and smaller. But he could also just move the panel or the screen further and further away. It would be the same thing, right? But then as he moves it away, for you to maintain sight or continue to be able to identify the words, he would have to scale them up by this factor. That's hopefully clear, right? It's pretty straightforward in a way. So scaling in size is one of the things that can somehow lead to trouble in your eye tracking studies, but it's not the only thing. Another thing would be having objects that are more visually prominent or salient, because they are also easier to identify in the peripheral visual field. So if you scale up in size and contrast, for instance, then it's easier to detect things. On the other hand, you have something like this flanker effect, which could then bring down or lower the identifiability of an object again. So in a way, you cannot really say, just as a general piece of advice, how far away should objects be when you're designing your eye tracking experiment. It's not really possible to just say just make a distance between the objects of 2 or 4 degrees of visual angle, then you're safe. You cannot. I hope that's clear from what I'm trying to show here. There's more, of course, and probably everybody's familiar with this kind of example of change blindness. Yes?
Yeah, I have a question about the visibility of what's outside the fixations.
Yeah.
Because I think there's a difference between saying a
Sorry, I'm just
recognizable
going to
blur
move this. It's irritating.
or a recognizable blur as you have presented there, and something that's not recognizable, and a blind spot. And I was wondering, because I know Tim has written a little bit about this, and I'm quoting you, Tim, because what you're saying is that
You should.
we are not aware of the frenetic pace of our attention because we are effectively blind every time we saccade between locations. So my question is,
That's a different
are we
mechanism.
blind or are we just, what kind of blur?
They're slightly different things. So the blur in the periphery is when your eyes are not in high velocity motion, and when you saccade, saccadic suppression actually selectively suppresses the low spatial frequency, so the blurred edge, because your eyes are generally open when you're moving, and if they moved and you didn't suppress that, you'd see the world actually swim in front of your vision. So what that is actually your visual system shutting down effectively for about 100 milliseconds across an eye movement. But that's a different process to what's happening in the periphery when your eyes are stable. In one
But our eyes, are they, well, I know there are smooth pursuit movements, but our eyes, how often are they?
3 to 5 times every second. It's usually about, say 3.5 times a second your eyes will move. And they're actually in flight for about 100, 120 milliseconds depending on how far they're going. But it can work out to be about 1/5 of your awareness is suppressed due to saccadic suppression. But that's independent of what's happening when you're holding fixation, trying to make sense of things in the periphery.
Okay.
Yes.
I hope you got your answer. Obviously, the sensation or the phenomenology of perception is very different from what's actually going on. we don't really experience a blur, and you aren't aware of saccadic suppression either, usually, I guess. Actually, maybe we shouldn't go into too many detours, but I think an interesting thing about eye movements is we usually think about it as sort of a device for attention, but as far as I understand, the reason why we actually have eye movements is to avoid motion blur in the first place, right? So if you're moving around as a foraging animal, for instance, one of the problems is that when you're moving your head, the gaze camera, whatever you call it, will simply move around and it will create a motion blur. So the way to avoid that is by simply coming up with something like eye movements. So you can maintain a fixation on something while you're moving your head or your body. And animals that don't have eye movements have to compensate in weird ways, for instance, by keeping the head still while moving the body. Maybe you can think of an example. Owls, pigeons. They're like putting the head forward and moving the body like this. I don't want to impersonate it. So the basic idea is they are maintaining a steady visual image while moving the body, right? So, yeah.
I know this example. I've always wondered, what do they do then when they fly? Because obviously
I was wondering about that too.
They,
but the biologists to
they
describe
don't need
it,
to stabilize because they're using the optic flow field.
Okay.
They're using the motion to actually stabilize their movement. But when they go into land, they have to basically aim at it because that's the point of expansion. But as they're walking, they need to do that bobbing because they don't have the continuous flow field.
So we are lucky that we don't have to walk like pigeons. That would look funny.
Yeah, so thanks to
Well,
eye
useless
movements, we
on
look
videos.
cooler. Okay, so back on the track. I'm trying to outline some different boundary conditions here, as you probably noticed, and well, one of them is also this here, which you're probably already familiar with. Even if you are looking at a particular location, we can't really say whether you have processed it or not, right? So probably everybody's familiar with blindness. Can anybody see what's changing here?
The shadow.
The shadow of the chopper is changing. Right? It's very hard to actually process that. Anyway, this brings me closer to what Josh was actually talking about. So this guy called Posner showed that the mental, what should we call it, the inner window of attention does not necessarily have to correspond to where your eyes are located. So you can have overt attention. If we say that you're fixating here with the crosses, then your inner mind's eye is also attentive to that area, but you can decouple it. You can keep fixating here while having attention to some other object. That's called covert attention. And at the same time, you can have something called focal attention on one object, or you can distribute it over some area. And these are somehow problematic when you're doing eye tracking, because you want to assume that people have focal attention and that it's overt. This is the main assumption that you're making. People are fixating here and they are attending to that particular object. So if you're studying reading, for instance, you hope that when people are reading the text, they're fixating here and then they're processing this word here. And as they move along, fixations and attention are somehow moving jointly. That would be perfect. That's the eye-mind assumption. But there are other problems. For instance, the fixation could move ahead of the attention, and in fact, I think this is what's actually always the case. Before we move the eye, the inner window of attention, or whatever we want to call it, has actually changed to the location that you will next be fixating on. So if I'm fixating on you, and then next I fixate on you, for instance, well actually I can't fixate that far, but I fixate you and then on your coffee mug, just before I change my fixation, my inner window of attention has changed to the coffee mug. So this is in a way always the case. But you could also have a different effect, that this is where it's lacking. What I was actually talking about is this situation here, where the window of attention is moving ahead, right? And what I was showing you before is this situation where the fixation moves first and attention somehow stays behind, lingers behind. So you keep processing something that you looked at before. And this is typically also the case in reading, as far as I understand, that you keep processing the words that you have just looked at, and you're also already processing the next word that you will be looking at. Now, most of this stuff has been studied in reading research, and when you're doing eye tracking on, for instance, decision problems, I mean, you're just left wondering how much of the eye movements that we capture actually map onto what people are currently processing. It's maybe harder to show in decision making, I don't know. But in any case, the main conclusions from what I tried to show you here is the strict eye-mind assumption. It's obviously false, right? We are not always processing what we're looking at. That's totally clear. And the Houston Carpenter assumption, they are literally stating there is no appreciable lag in what we're fixating and what we're processing. Well, no, let's not believe in that. But when we're doing eye tracking, we still need to somehow make the assumption that people are or have at some point cognitively processed what they were fixating. So we could say using a relaxed eye-mind assumption. And what I've tried to show you is that this may or may not be valid in different situations. It is possible that you can fixate one location and process something in the visual periphery. It could, for instance, depend on the size and the contrast of objects in the visual periphery. You cannot exclude the possibility that you've actually identified an object just because you did not look at it. And, well, I think my main message is, even if you have set up a nice behavioral experimental design to capture this particular dependent variable attention that you're interested in, you still have to be aware of these boundary conditions. Okay. So far so good. That was the eye-mind assumption. What I want to use a little bit of time talking about is actually what I termed the eye-object assumption. And this may or may not be relevant depending on how you do your research. But as I said, 99% of eye tracking research, I believe, relies on this assumption for the simple reason that it's extremely convenient. And convenient is good. So when you do your eye tracking experiment, what are you actually capturing? Well, essentially you have like a time series type of data. You have your X and Y position and a timestamp for every single time step while you are capturing eye movements. So you have a very huge amount of data that you somehow need to put into a format where you can process it. And the main thing that most people do is they simply draw an outline around some objects, and then they say, if you fixate that object, or if the fixation is near to that, then we assign that fixation to that object. In other words, the eye-object assumption, or whatever we want to call it, is the assumption that there is a unique relation between a fixation and one object. Okay, this deserves maybe an example. So here's an example. We put some participants in this experiment here to the task of choosing between different junk foods. So there are 3 different kinds of junk food. You just have to choose, and then we obtain a pattern of fixations. And every dot here corresponds to a fixation. Now we want to know how much did these participants look at object 1, 2, or 3. But what we get is actually these clouds here of fixations. So how do we map that? Well, we simply draw an outline that corresponds roughly to the size and shape of each of these objects here. And then we say every fixation which is landing within this boundary is assigned to that object. If a fixation falls outside the boundary, we'll just forget about it. So this is what I'm trying to say, or what I mean when I'm saying there is a unique relation between the fixation and the object. Right? Any fixation falling in here is mapped onto this object only. We don't map this fixation to that object. Right? And all the fixations that are somehow outside, we'll just forget about. So as you probably notice here, maybe there's a slight problem. I mean, we're missing something, right? A lot of fixations that we're just throwing away. So how can you solve this? It's pretty straightforward. Just make the boundary bigger, right? Problem solved. Now you're capturing these fixations. Well, there are actually still a few that are escaping here. But what then happens if you have a slightly different kind of experiment? Like this here. It's from the same study actually. We manipulated the distance between the objects and obtained this fixation cloud here. What kind of areas of interest would be meaningful to assign? Well, we probably don't want to have these areas of interest overlapping. So what's an ideal size? And how do we know that we aren't capturing wrong fixations within this boundary here? So the problem that we're actually facing is that fixations are not perfect, perfect to the object. Even if, let's say, even if the mind had a unique relation between fixations and objects, eye trackers are noisy, or tend to be a little noisy. So eye trackers have what you could call an offset. Even if I fixate exactly on this point here, the eye tracker may measure the fixation location a little to the left or a little to the right or above or below. So when you have enough fixations, this then gives you that a cloud of fixations or a distribution of fixations over that object. It's not perfect. And this basically means that if you have objects that are close to each other, the distribution of fixations is probably going to overlap to some extent. Now this violates the basic assumption or auxiliary assumption that there is a unique relation between an object and a fixation, right? Or at least it creates the problem that now we've been counting some fixations wrongly in this situation. So what can you do about it? Well, for one, you can use a better eye tracker, but of course the main thing you probably want to do if you can is position these objects further away from each other, although that's not always possible. So let me illustrate this in a more simple example. Let's imagine in a single dimension we have object A and object B, and over these objects we have a fixation distribution. And the reason where there are triangles is because I don't know how to make a Gaussian in PowerPoint. But otherwise it would be a nice Gaussian over there. And you can see they're sort of overlapping here. Now, we want to know how many fixations are there to object A and object B, so we draw an area of interest. We said this is the range where we will count fixations to B, and this is a range where we count it to A. Now this leads to the curious situation that for counting A, we will have more false negatives than false positives, while for B we will have more false positives than false negatives. Now, one way that you could possibly deal with this is simply narrowing the area of interest. And now it will be true for both object A and B that the number of false negatives is higher than the number of false positives. So if we assume that all the objects have the same AOI margin and the distribution of fixations are overlapping, and also that there is actually a difference in the distributions, then having large areas of interest will attenuate the effect size. So you want to think about that if you use this particular method. And if you considering to start using eye tracking, it's very, very likely that you will end up using areas of interest because it's simply extremely convenient. You can think about it as a signal detection kind of problem. The more noise you have in the distribution, the wider it is, the more they will overlap, particularly when they're close to each other. So the best case is when you have very little noise and the objects are positioned far away from each other. So if you're free to actually design your own stimuli, for various reasons, you may consider to put or ensure that they are far away from each other. And for other reasons that they are maybe not discriminable in the visual periphery. So for instance, think about flankering, the size and the contrast of these objects. But I want to finish that part here with an example. So
Can I ask a
Yeah,
quick question before we move on? So are there any methods for using some statistical assumptions in modelling these areas of interest in a somewhat more a priori way rather than just setting the boundaries? Because the first thing I think as, you know, I'm not getting the p-value I want, I'll change the size of the area of interest until I do. Is there any way you could use the expected statistics of fixations to avoid that? Are there?
yeah.
As a very naive eye tracking, I don't know anything about eye tracking specifically. One of the
So-
worries I have.
Ideally, maybe we should sit down and develop a Bayesian approach to this or something. I'm sure there's a better way to do this. When I was presenting this paper, like first time like a year ago, one of the participants or in the audience, there was a guy who's like, "Thank you for showing me how I can fish some p-values." I mean, it was a joke, right? But still, yeah, it matters. And
I mean, it's
people.
very good researcher degree of freedom.
It is just giving you degrees of freedom in playing around with your data and obtaining results that are more or less aligned with your hypotheses.
But there's no models, standard models.
You can do it probabilistically, so assigning a fixation based on how near it is to one object compared to another, so you get the probability of it being in one AOI compared to the other. And they call that fuzzy AOI, so they don't have a hard boundary. It's based on a Gaussian.
Yeah.
It doesn't. People don't use it that often. Usually, designing the stimuli is, where you would think about the areas of interest before. But in natural scene viewing, where things are close together and they're spread in different ways, then it may be more sensible to do that sometimes.
Okay.
Yeah, so the fuzzy AOI or attentional landscape approach, just replaces the hard boundary with a Gaussian over the fixation.
Yeah, and a Bayesian thing would be exactly what I'd be indicating. Could be
Yeah.
interesting because there you have some sort of priors on your.
Yeah, but the
How
problem
do you
is,
get the priors from the eye movement?
Well, you wouldn't get priors from the scene.
Yeah, so that's the probabilistic.
Yeah,
You basically create
yeah.
a probabilistic landscape of
Yeah.
where the objects are.
Yeah.
And they
exactly.
blur, so you
Mm.
make that
Yeah.
more continuous.
but I mean, just replacing a hard AOI boundary with a Gaussian doesn't actually
No.
solve this problem,
No.
right? Because you still have some degrees of freedom in what is the standard deviation of that Gaussian.
Yeah, that's what I mean. That's
Yeah,
a priori.
so that doesn't actually solve it. I mean, it
Yeah.
changes the problem maybe, or maybe not, I'm not sure. But
Yeah, and if things are close together anyway, even if you can say for sure that you're in one place or another, as we heard from your earlier talk, you could be attending to the other thing even if you're really sure. So
Yeah, exactly.
better to make them further away to begin with.
Yeah.
Yeah.
Yeah,
Okay, thanks.
that
Alright,
would also be my
good.
take. Well, actually, I want to just finish with an example, something that Sonia and I are working on. So this is from an experiment where people are making inferential choices about which product is the more healthy, and we have simply manipulated the statistical correlation between some cues in the environment, the keyhole here, and the organic label. And we just want to know, can people learn in an unsupervised manner that some cues are correlated, and would they then start using these cues in a heuristic way? So we run the study, we obtain the data, and now we need to decide what sort of AOI size do we want. We want to know whether people have looked at this keyhole here. And as you can see, we don't actually have the possibility to put the keyhole somewhere else, right? It's right next to the text, which is somehow irritating, but that's what it looks like in the natural world. So if you make the AOI larger, now you're pretty sure that you will be capturing some of the fixations, maybe even fixations to the price and to the title here of the product. And with a brave effort from Sonia, we've actually counted manually coded fixations to these objects and then used different AY margins to see what happens with the number of false positives and negatives. So in the situation where we're using a tiny or an AY margin, so the AY is the same size as the objects, you see that we have false negatives but no false positives. So we are losing fixations that should actually have been assigned to these objects. If we extend the AY margin just a tiny bit by 0.15 degrees of visual angle, we have fewer false negatives, but somehow now we are starting to see some false positives. So fixations that in our hand coding or qualitative coding have actually been assigned to other objects. If you go on extending the AY margin to half a degree of visual angle, so you have very few false negatives, but now suddenly you have quite a lot of false positives. So fixations that rightfully belong to other objects. And I should have put in the results that vary as a function of this. Actually, that would have been which one was the nicer one. The one more in support of our hypothesis was the 0.5 margin, right?
Yeah.
Yeah. So should we go for the 0.5 AY margin because this one is the one that actually fits our experimental hypotheses?
Actually, I think it was the opposite. It was the zero.
The zero margin?
Yeah.
We can pick the zero margin, right? Probably you don't want to do it like that, right? So, well, that's the kind of problem you actually face. Mostly, I guess, people wouldn't actually hand code it and then check the number of false positives and negatives, but we thought it was interesting, and well, that's just an example of what happens. So, which one is the right size? Actually, I don't really know. I guess we can think about, in some cases, maybe we even want to impute fixations, because somehow either you have false negatives or you have false positives. You can't really, there's like not the perfect boundary for these objects. Yeah?
I don't really get how you manually annotate. I get how you manually annotate, but
Yeah, it's exactly what you're doing in your mobile eye tracking.
yeah,
So we manually annotate.
if you have assigned an AOI, let's say in 3 different sizes, how do you define your manually annotated criteria? For your criteria for manually annotating. I just don't get how you can get it.
How do you know what the actual canonical fixation on the object is?
Yeah, that is a manual annotation.
But that's subjective.
So that's we call the criterion, or the manual annotation is the criterion, right? So we, of course, it's also not maybe true necessarily, but it's probably more true than the automated AY assignment.
But when you manually annotate, you put up some criteria that say, okay, when it's within this circle or within this square, right?
Yes.
You put criteria up in exactly the same way as you do when you put up an AOI in some sense or another. So how I don't get how you can get different values between your automated AOI analysis and your manually annotated AOI analysis.
Because when you're manually annotating, you can take into account that this person has a slight offset to the lower left, for instance. Or that person has no offset. Or this fixation falls exactly between the text and the keyhole label. So maybe we don't want to count it. Or this is actually...
Then you should,
Sorry?
If you have a false offset, for instance, or you have these kind of, then I guess you should correct your eye tracking data instead. It's so vulnerable to kind of like researcher bias to do it the other way. I guess this one would have been on the.
No,
that's
I
basically what you're saying.
completely agree. It's extremely vulnerable in so many ways. Let me give you another example. So if you see there is a fixation to the text and it's followed by 2 more fixations to the text. But the first fixation is right next to the object of interest. Now, given that the following fixations are actually on the text, so they are completely horizontal, it's probably a fair assumption that even though that first fixation was almost on the object of interest, it's actually not. Right? Does it make sense? So that's like basically infer something about the association of that fixation to an object based on what comes before and after. And based on what you know about this participant's offset, for instance. Maybe you know that this participant was slightly offset towards the upper part of the screen.
Makes sense.
But no, I mean, it is a problem. So there's a lot of degrees of freedom in the manual annotation and in the AY assignment and in how you want to do this. And I don't think we have a perfect solution to this, although I'm very curious in developing some better methods for this.
I've never done eye tracking, so this is a very beginner question, but could you go back to the slide with the product?
Yeah.
I'm just wondering if you're most interested in looking at the symbol and whether they attend to the organic symbol or the keyhole.
Yeah, that's the only thing we want to know basically. Are they looking at this object here or that
Right.
or this keyhole here?
So, but wouldn't it be a stronger design to have the packaging be more uniform? Because how do you control for that? Because like knowing that, for example, that seriously strong red package isn't more interesting visually and therefore drawing more attention to that sign. I mean, how do you?
Yeah, no, you're absolutely right. So if we had only one critical trial, then this would have been a humongous problem, right? Because it would have been confounded by the stimuli in the background. But fortunately, we have more than one critical trial, so hopefully, and if we had been better researchers, maybe we would have controlled for that, but at least we're assuming that over a number of trials, some of these differences will randomize away. So we are thinking of every single critical trial as a random instance, where there may be some factors that make it more likely or less likely to look at any of these objects. But ideally, with enough trials, with enough variation in them, this randomizes away. But we could also, I would probably never do an experiment relying on just one critical trial. But if you did that, then you would have this problem, for sure. Okay, so, yeah, interesting example. So basically what I want to argue is if you want to use eye tracking to measure attention, it's in a way to think of it as a signal detection. Either something is fixated or not, but what you want to know is whether it's attended to, or at least you could claim that it's been processed or not processed. And well, if you have a true positive, so it's fixated and processed, well, then you have to make these assumptions that the eye mind and eye object assumptions actually apply. So that people process what they're fixating, and what they're fixating or the fixation is uniquely assigned to only one object. Both assumptions are wrong, but you still somehow have to make them. And what I've been trying to show you is basically what's going wrong in these two diagonals here. So when it's either not fixated, but you can still process it, that would be something like problems with the AY assignment, or it could be something like the visual, the contrast or size and so on has been scaled up so you can identify it without looking at it. Or the situation where you fixate it but don't process it. For instance, the chopper shadow example, you can look directly at it, but you don't see it in a certain sense. So that's the kind of problem you're facing. So to conclude, I do believe that you can use eye tracking to measure attention, but you can also measure a lot of other things. And whether you use it to measure confusion, boredom, emotion, fatigue, interests, or whatever it is, my personal take is that it really depends on how you construct the behavioral part of the experiment. It's not the eye tracker per se that does the trick, it's the behavioral part of the experiment. Now, assuming that you have done this correctly, then I personally think it's important still to keep in mind that you have to make these auxiliary assumptions. You have to obtain valid and reliable data, of course, but besides that, then at least be aware that mostly you will make this eye-mind assumption, which is wrong, and you will also make this eye-object assumption if you're using AYs. But maybe there's a way to get around that. So, that was, I think, what I had to say.